Okay, so today I'm going to speak about inverse eigenvalue problem for symmetric doubly stochastic matrices. This is a fairly recent work with Tomasz Kania from the Institute of Mathematics in Prague, Czech Republic. I'm actually not a specialist in the subject at all. And as already Karol said, I got in touch with him because of the paper that him and Renard just published, or at least it was on archive by then. So I looked at it and I was like, oh, people from Oxford doing similar things, and I just got into it. So I thought that he might be one of the specialists in the area, and it turned out that we both very new to the inverse eigenvalue problems, and we got there by accident. But I think it will be a part of the story of this presentation. Because this is a network seminar, I thought that, so I have to do the full screen. I haven't done the full screen, so sorry for this. So I thought that the first slide will be the most network graph related. So I'm just going to give you some examples of some special matrices, and I'm certain that everyone is familiar with these matrices, and I thought it's just worth bringing them because of the topic as inverse eigenvalue problems. So when we start with a graph, simple without any loops, say undirected, we can have an adjacency matrix, right, which indicates if the pairs of vertices are adjacent or not. And then we have a degree matrix, which tells you what's the number of edges attached to its node. Then we have a Laplacian matrix, right, which measures the extent a graph differs at one vertex from its value at nearby vertex. And Laplacian in particular could be written as the difference between the degree matrix and adjacency matrix. So Laplacian matrices are nice. They just they are, in this particular case, they are symmetric, positive, semi-definite. Every row of a Laplacian matrix sums up to 0. And in particular, 0 is the smallest eigenvalue of a Laplacian matrix. And so you could study Laplacian matrices as Karol and Renard have done through this inverse eigenvalue problem business, which I'm going to speak about later. However, I'm going to focus on different matrices, not at Laplacian matrices. I'm going to focus on matrices which are usually related to the Markov chains and their transitions, right? So here maybe it's a bit misleading that the graph has been taken to be undirected, but I just wanted to just have some sort of an introduction of the other matrices, like the most simple possible. So transition matrix, the stochastic matrix, a different name is a transition matrix, probability matrix. So it gives you the transition of Markov chain. So what is the probability from going to one state to another? So these entries of the stochastic matrix are probabilities, so are between 0 and 1, and each of the row sums up to 1. And you can get a very easy example, but not the most interesting one. If you take the adjacency matrix and a degree matrix, you take the inverse of the degree matrix and times it by the adjacency matrix, and then you will get an example of a stochastic matrix. Here, this construction is working because I took G to be undirected, so that A is symmetric in this particular case. Then we have also doubly stochastic matrices, which are not very similar to the stochastic matrices, but what those are. So if you take the transpose of a stochastic matrix and it's still stochastic, then the matrix is going to be a doubly stochastic. So here, rows and columns, they sum up to 1. So each row and each column sum up to 1. It is not necessarily that they are symmetric, neither of those, right, of course. And however, if a stochastic matrix is symmetric, then it's clearly doubly stochastic. Also, doubly stochastic matrices are also in the literature. You can find the name bistochastic. So this is the terminology that people come across. Okay, so what's the focus, aim, motivation I mentioned that the motivation doesn't come from matrices like directly. As I mentioned before, I started this research by accident. So my colleague at Portsmouth and by then our PhD student, so we wanted to generate Markov chains, like symmetric Markov chains. We wanted to generate the probabilities, the transition probabilities in some sort of a random manner for some sort of a simulations. I don't even remember exactly what the simulations were for, but we thought, okay, this is definitely done in the literature. So let's just have a look at this problem. And then I noticed that it's actually, if you want to generate transition matrices from, say, the set of eigenvalues, so you would like to make those eigenvalues some random variables, and then you generate them via some sort of a computer program, and so that you automatically obtain a transition matrix, is actually not trivial at all. And getting matrices of a certain properties from eigenvalues is known as the inverse eigenvalue problem. So the aim of this talk is to introduce a fairly simple algorithm that will allow us to generate a symmetric Markov chains, like the transition matrices for those chains. And then this comes, again, as I said, this involves all this matrix linear algebra theory, maybe not by total surprise, but it is an accident that we actually managed to wrote the paper, and it's all sort of a new findings, because I was certain that this is probably well known. Okay, so let me now go very linear algebraic. We have the inverse eigenvalue problems, and I mentioned before that inverse eigenvalue problem for a matrix with property P. This is, I'm just using this terminology, property P. Later on, probably I'll just mention what the property of the matrix is. So an inverse eigenvalue problem for a matrix with property P is a problem of finding necessary and sufficient condition for a list of numbers to become a spectrum of a matrix that has this property P. And if we take a list of numbers, say sigma, because sigma usually good letter to represent the spectrum. A list of numbers, sigma, is said to be realizable or P-realizable if there is a spectrum, if it is a spectrum of a matrix with the studied property, right? So if we say that if we study an inverse eigenvalue problem for example, for matrices with non-negative entries, then a list of numbers sigma is going to be realizable if it is a spectrum of a matrix that has non-negative entries, right? And this particular problem was the first, if we look back in the literature, right? So I've done a bit of a research on the history. So actually this was first, this sort of a problem of getting, of generating matrices from eigenvalues was due to the Kolmogorov, the probability Kolmogorov guy. It was in 1937. And this was originally stated in the context of not non-negative matrices, but stochastic matrices. However, in 1981, Charles Johnson showed that those two are equivalent problems. So this is why I put this non-negative inverse eigenvalue problem as the first one that was mentioned, as there is this equivalence for the stochastic case. Okay, and this problem is really difficult, and it's still unsolved in full generality. And this is what probably is shocking. It was shocking to me. And then I discovered that, yeah, it is really difficult. In fact, if your matrix is greater than 2 by 2, it's already non-trivial. So it remains unsolved in full generality. And it was fully solved for n less or equal 3 by Levin in London in 1978. And for n equals to 4, it has been solved by Mission and Torre Mayo with collaborators. This is using different methods. I actually myself knew only about this Torah Mayo et al. Paper, but then I was reading the great exposition, great survey on all the inverse eigenvalue problems, focusing on non-negative one by Johnson, Mary Juan, Paparella, and Pisonero, and this is called, the paper is the non-negative inverse eigenvalue problem. And you can see, you can read about the history of it. And I used a lot of facts just directly from this paper, because I like to sort of present something starting from the historical motivation. So I mentioned first that I'm starting with non-negative matrices. So what are the properties of non-negative matrices that are sort of important, in particular important to this research that I have done? First of all, I say non-negative matrix. Here I mean a matrix with non-negative entries. Sometimes people use the same terminology to matrices which have non-negative eigenvalues, or equivalently can be written as a product of a matrix with its transpose. So I'm here, I'm just fully working on the matrices which have which are entry-wise non-negative. So there is a famous classical Frobenius Perron theorem, and it states that if A is such a matrix, so in this case non-negative entries, that it must have a non-negative eigenvalue, which we refer to as a Perron eigenvalue. And this eigenvalue also gives you an upper bound for the absolute value of any other eigenvalue of this particular matrix. And this eigenvalue also has a eigenvector that it corresponds to, of course, and this vector is often called the Perron eigenvector. So now, because my focus is, as I mentioned before, on symmetric stochastic matrices, so symmetric allows me to work with real spectrum, and also like symmetric stochastic gives you a doubly stochastic matrix, as I already mentioned. So it can be shown that a stochastic matrix has this Perron eigenvalue to be 1, and this corresponds to the eigenvector which has ones everywhere. And so this is clearly from the definition of the, I mean, that showing that it is that lambda 1 equals to 1 is a Perron eigenvalue. It's maybe a bit more tricky, but we know that it has to correspond to the eigenvector so that it has all ones. It just comes from the fact that its rows sum up to 1. So if you take your matrix, you take the vectors of 1 and you times them together, then you literally what you're doing, you're summing up every vector, every row, so that you're going to get ones. So you can see that this is the eigenvalue 1, which has this corresponding Perron eigenvector to be ones, right? Of course, if you wanted to make it unital, then unit vector, then you would just divide it by 1 over the square root of just a n. Take into account that n, we have the A is the n times n matrix. So what are the other properties that are sort of important in this talk? So next property is the trace of the matrix, right? We know that if A has non-negative entries, that a trace or any power of this non-negative matrix, they have to have a non-negative trace. And we know that due to the tracial property, this has to be the same for the sum of eigen values. So we have that the spectrum of matrix A has to satisfy this particular condition, and this is a necessary condition. And this condition is important because I believe that the first people who came up with a sufficient condition, first sufficient condition for a matrix, for a spectrum, for a list of number to be realizable for this non-negative entries property, comes from this particular condition. It's a slight modification of it. So I'm going to demonstrate it now. So the first known to literature sufficient condition for the non-negative inverse eigenvalue problem. In fact, here, if I may bring back the problem. So here, let me again show the problem, right? So finding necessary and sufficient condition for a list of n numbers. So now if we have complex numbers and real numbers. So if we are speaking about real numbers, then we are going to call it a real something inverse eigenvalue problem. When we speak about complex, then we are just going to drop the name complex. So the first known to literature sufficient condition for non-negative inverse eigenvalue problem, and as I mentioned here, it's in fact this real one, because the list is restricted to be real number, is the following. So we take the list or a set of real numbers, and we put the condition so that the first one is the greatest, and is the greatest by the absolute value. So if you take the absolute value of any other one, it is the greatest. So only the first value is positive, and all other values are non-positive, right? So they are either negative or zero. And moreover, due to this condition, we are going to take that sum of all the eigenvalues, or all those numbers here, is going to be greater or equal 0. So this is the sufficient condition, not mine. I'm going to mention who came up with it. And so this condition first was introduced in 1949 by Sulimanova. And so in this paper here, which I tried to access, but it's really difficult because it was just, I think, published in a Russian journal. And however, in some of the sources, some of the papers, people claim that even though this condition was stated, and there was a proof that it actually, this set sigma n is a spectrum of the non-negative matrix, given this condition, that it was sort of a loosely proven. So it wasn't like a formal proof. And the formal proof is known to Hazel perfects from 1953. So this is the first known sufficient condition for this inverse eigenvalue problem for matrices with non-negative entries. And again, it's very important in this particular study or in this talk. And so let me sort of repeat one thing here is that only first eigenvalue is positive, and all other ones are either negative or 0. And because, as I mentioned, this condition is sort of important for the work that I've done, let me make a definition which originally comes from 2016 Johnson and Paparella. I just slightly tweaked it to adapt it to like the further theory that will be required to my result. So a list of numbers, lambda 1 up to lambda n, is called a Sulimanova spectrum whenever, if you take the sum over this list, it's greater or equal to 0. And first number is greater or equal to 0, while all other numbers are less or equal to 0. And there is further terminology that we can call this spectrum normalized if there is we can order those eigenvalues. So we take lambda 1, then it's greater or equal lambda 2, lambda 3, so on and so forth. So this is what I sort of call the normalized spectrum. Otherwise, if it's not normalized, I'm just going to only assume that lambda 1 is positive and it's on the first is the first entry of my list, and all other ones are negative or 0, but the ordering is sort of arbitrary. So because this Sulimanova spectrum, in fact, is the same as this condition, so we can see that it was already shown by Perfect that this list is realizable as a spectrum of a non-negative matrix. So further, there was a result in 74 by a Czech mathematician Fiedler, who shown that Sulimanova spectrum is realizable by a symmetric non-negative matrix. So here adding this property of being symmetric. Then about 5 years ago, apparently this is a private correspondence, but I didn't, I read about it in one of the papers. Johnson, Marijuan, and Pisonero thought that it might be possible. So they stated this problem is every normalized Sulimanova spectrum realizable by a doubly stochastic matrix. So here our symmetry is dropped, and then it just focused, can we get, just given this list of numbers, can we construct a doubly stochastic matrix so that it has a spectrum to be the list which satisfies this condition. So in 2016, Johnson and Paparella, they managed to prove that for any Hadamard order, the Sulimanova spectrum sigma is realizable by a symmetric doubly stochastic matrix. So in fact, there is this symmetric property here as well. And and this sort of a construction was nice due to that it was actually giving you the matrices. For example, the Fiedler's construction it wasn't a constructive. You couldn't construct the matrix. You could only prove the existence. And so let me sort of recall here that Hadamard order. So is an order if so it's an order n if there exists a n times n Hadamard matrix. And the Hadamard, there is a famous, very old Hadamard conjecture that states that Hadamard matrix of order, there is a Hadamard matrix of order 4 times m for any m natural. So here I'm going to modify this problem a bit to the one which was stated by so that Johnson, Marijuan, and Pisonero stated. What I'm going to say, okay, so is every normalized Sulimanova spectrum realizable by a symmetric doubly stochastic matrix? So I'm just here just thinking, okay, so they have this one. What if we add symmetric? Was there a reason that I just put here doubly stochastic after Johnson and Paparella actually got a symmetric doubly stochastic matrix? So let me state this problem, and this problem has a negative answer because, and I only stated it in the presentation so that people can see that it does not hold. So if I take dimension 3 and I consider a very simple list having 1, 0, and -1, so this clearly sums up to 0. So it is a Sulimanova spectrum, a normalized Sulimanova spectrum. So if it was realizable, then they would be a symmetric doubly stochastic matrix. And if a matrix is symmetric, then there is a famous spectral theorem. So we could write it as a sum of the those rank 1 sort of operators matrices. And what we would know here. So here E is the eigenvector that corresponds to 1. So it has 1 here. That 1/3 comes from the normalization, because normally the unit eigenvector this corresponds to eigenvalue 1 is 1 over the square root of 3. So this is why the 3 is there. And then U has this form, a bit more general, but because we know I want this to be a unit vector, so that this is why it has those entries. Moreover, we have to assume that those E vector and U are orthogonal, perpendicular, so this condition has to hold, right? So now what happens if we actually calculate the entries of this matrix A? Because we can just do it by multiplying those vectors and subtracting. What we are going to get at the main diagonal is the following. And this shows, if you look at it a bit closer, that those guys, we know that they, here we have the trace 0, right? And also those has to be, so they only can be 0 in this case, right? So they have to be, so because otherwise they wouldn't be they wouldn't be non-negative. So what we get that actually U1 and U2, they have to have those values, which yields that the third entry has to be 1 over the square root of 3. But if I look now at this condition, right, because this E vector and U vector is supposed to be orthogonal, then I'm going to get this if I do the dot products of those two vectors, and this is non-zero, and therefore they cannot be orthogonal, so it is impossible to have a symmetric doubly stochastic matrix so that it has this Sulimanova spectrum. Therefore, this problem with a dagger there immediately for negative order, or it has a negative answer. And in fact, what I showed here is just a simple proof when n equals to 3, and it has been, of course, shown for any odd numbers, and the reference you can see underneath here. So I sort of came across this, done this calculation myself, and then I also found that yeah, there was actually nice. This was already sort of a known and proven for any odd n. Okay, so this gave me a bit of a motivation, or I should have said, gave us a bit of motivation. So because we know now that the problem was 0 here, right? So the problem was that our whenever our list was equal to 0, then we could have then we couldn't have the positive answer to the non-negative, sorry, to this particular problem. So now what we modified, we were like, okay, so let's take an arbitrary number delta. And let's say that now we are going to call a set of numbers, a list of numbers, a delta Sulimanova spectrum. If their sum is greater or equal than some non-negative delta, and similarly to the Sulimanova spectrum, all guys here from lambda 2 up to lambda n are either negative or 0. And because we are going to study this problem for stochastic matrices, I already input lambda 1 to be 1 due to the property that I have demonstrated earlier. So now we are stating the problem, okay, take delta greater than 0. Can every delta Sulimanova spectrum be realized as the spectrum of a symmetric doubly stochastic matrix? So assuming this, fixing first some delta greater than 0, can we always find a matrix which is doubly stochastic and symmetric, and it has this Sulimanova spectrum as its spectrum? So we obtained the results. So fairly recently published in May in linear algebra and applications. So we managed to show that a half Sulimanova spectrum will do. So if I take delta to be a half, then there exists a symmetric doubly stochastic matrix with spectrum sigma, and we gave explicit construction of this matrix. So here let me tell one more. Let me tell you here one thing here. So so the proof is relatively straightforward, but I know that everyone says that usually. But however, this uses elementary linear algebraic tools, and so I sort of decided that it would be nice to sort of sketch it to give you the idea how how we got this number. And in fact, if maybe this will give you an idea how to get a better delta than a half, right? So okay, so how would you sketch how this proof could be sketched so that maybe if you come up with a different matrix, then you could get a smaller number delta than a half, and then perhaps just get a better result. So so if we give an arbitrary half Sulimanov on the spectrum, what we plan to do? So this will be our assumption about the list. So now the plan of construction is the following. So we would like to construct our matrix P, which is supposed to be symmetric and doubly stochastic, just via you usually have, whenever you have the eigenvalue decomposition, this is what form you would get. And here our matrix is symmetric, so we know that it would have to have this form. So therefore, we are only interested in getting a Q, and the form of matrix P will be just automatically given by this formula. So here, so symmetry we've got for free from this form. Now, how about summing to 1? Summing to 1 we will get as soon as Q will have the first column to be a normalized vector, unit vector with all the ones, right? Because then we know that this gives us that if we multiply matrix P by 1, because it will be an eigenvector, then it will correspond to eigenvalue 1. So we'll get each row summing up to 1. So the tricky part is non-negative entries. So how to get this particle matrix to get non-negative entries, given that we made the assumption about spectrum to be Sulimanova. So I might skip this slide because it's just based on the calculations, and I might just give you the sort of an idea of the proof. So how did we come up with this matrix Q? So because I study random walks on a, let's say, daily basis, we were like, okay, so if we take a random walk on the circle, so it has the following transition matrix. How about if we just take its eigenvalues and eigenvectors and try Q, to be that, just why not? Just a total sort of a guess, because of the nature that I deal with random walks on a sort of a regular basis. So okay, so we've done that. So first of all, it is because the Pn, so this transition matrix is a circulant matrix. And I don't know if people are familiar with the terminology circulant matrix. You might be familiar with the terminology circulant graph. So circulant graph has adjacency matrix to be a circulant matrix. I think there is a question on the chat or somewhere, so I might have a look at it. Sorry. Yeah, just no worries. I've got okay. So let me continue. Right. So here there is a very nice sort of when we have a circulant matrix, there is a theorem that tells us that this circulant matrix is diagonalizable by a Fourier matrix, and so we always can get it of this form. However, in this case, the Fourier matrix, as most of you know, has the following entries. So they are like the roots of identity with some power, right? And so those are complex numbers here. So in fact, here we are getting a complex. So if we take our PNs, so we get complex eigenvectors, and sort of because of the nature of our problem, we would like to have a real rather than complex, right? And of course, you can also obtain the eigenvalues that correspond to it. So we, in fact, can write that Pn has this particular form. However, when you have a complex eigenvector, the real and imaginary part of this eigenvector is also an eigenvector that corresponds to the same eigenvalue. So, okay, so we just took the real and imaginary part of this eigenvectors, because they are also eigenvectors corresponding to the same lambda. However, they do not span just the whole Rn. So they cannot, and to remember that in order for Q to be an orthogonal matrix, its columns, they have to form orthonormal bases. They have to be orthogonal, right, and unit vectors. So then neither of those actually span it. However, if you add those together, if you add the imaginary and real part, then it's still an eigenvector that corresponds to the same eigenvalue. And if you just normalize it now, then in fact, it forms an orthonormal basis. So we can actually use it as the entries of matrix Q. So now we have our matrix Q. And just due to the previous slide, which I skipped, which was technical on calculations, we can actually now calculate our matrix P, how every entry of this matrix P looks, right? So this is the entry. So now what we would require in order to prove the theorem, we would require that this entry is greater or equal 0, given that we have some assumption on the sum of the eigenvalues. So now this is what we can have, right? So if I look at this, this is exactly like the entry. However, I just, so because this has to be greater or equal 0, I can times it by n and subtract 1 and then divide it by 2. So in fact, I'm going to get sort of this guy there. But because here in this, the entries of this matrix are signs, and we know that signs are greater or equal, are less or equal, they're bounded above by 1. But lambda j's are negative. So if we assume this, which could be translated that the sum of all the lambdas starting from 1 up to n minus 1 are greater or equal to -1/2. So this is our assumption from stating that spectrum is Sulimanova. So therefore, this bit is from the assumption, but we know that this has to be greater than that due to the fact that the sign is always less or equal 1, and those all the lambdas here are negative numbers. So this works, and therefore we managed to prove the theorem, right? So this is why I mentioned that the proof of the theorem is probably relatively straightforward. So now the algorithm that I promised at the beginning. So now knowing that we can construct a matrix that satisfies this particular condition, we are taking independent random variables, and we take them, we let them have probabilities supported on 0, 1. Then we take the sum of those random variables, we times it by alpha and divide it by Sn, so that all those lambda i's, they actually satisfy the Sulimanova condition with delta to be 1/2, right? So therefore, I can now randomly produce those lambdas and use the formula for the matrix that we obtained to randomly generate symmetric doubly stochastic matrices. So after the theorem has been proven, so we actually got this matrix P. Now the algorithm that I sort of wanted to get is relatively simple, and I can now randomly generate those matrices from the eigenvalues. However, of course, here I'm just only generating some sort of a subset of all the possible symmetric doubly stochastic matrices, right? So possibly improving delta from 1/2 to something better would actually make this alpha to be, we could modify then this alpha so that we would get more and more matrices, right? And again, I'm not sure if it's possible to get a better delta with just one matrix, right? Because here our matrix Q was the key, right? So the matrix Q was the key to this construction. And maybe, you can get like a family of those matrices and then join them together to actually prove this problem for any delta. So I promised in my abstract, I promised examples. And of course, so the problem of examples is that when I take n to be big and I'm not having any pictures, like a graph pictures, it would be hard to see. So what I can refer to is that I've written a code In the paper that you will be able to see in the references, so the paper that I've written with Tomasz Kania, we have added the supplementary material which implements this simple algorithm, and you can get these matrices, these doubly stochastic symmetric ones of any, when you specify n. And of course, as I said, just displaying these matrices is not that, you cannot really see that much due to, it will be much better to see some certain parts of a graph for that. So I might just apologize that examples are not that sort of a visual as I would have thought. I think we are at 50, and usually, because I'm also a seminar organizer at Portsmouth, it's where usually we are finishing the talk. So I'm just going to finish it with stating a few references that I have used for this talk. And thank you very much again for the invitation, and thank you very much for your attention. And yeah, thank you. So I can give now Karol, I guess.